Let's think about the test for exogeneity. We have very simple regression with a scalar and demeaned regressor. And so, but it may be endogenous. So we prepared an instrument that satisfies all the conditions. But we would like to test if the regressor was exogenous or not. Okay, it's pretty simple. We are going to think about the unrestricted model first. The unrestricted model does not utilize uncertain hypothesis, right? So that means the only moment condition we have is the IV, right? The instrument is the only exogenous variable in the unrestricted model. So the moment function looks like this, and then sample moment, of course, goes like this, and the weighting matrix does not matter in this case because there is only one moment condition for one unknown. So the weight, no matter what weighting matrix you use, the result will be the same. So I'm not going to worry about the weighting matrix, and I'll just simply use identity matrix. And then the criterion function will look like this transpose weight in the same thing, but actually it is weighting matrix is identity and g the moment function is scalar, so it is too simple. It is just square, right? Nothing much to talk about. So we did it a lot in the previous chapter. I'm going to skip the details. We know the closed form solution. If you just take the first order condition, okay, let me write down the first order. First order condition looks like this. So this was the first order condition from the GMM chapter, okay. And then in our case, this is identity. This is scalar, and it does not mean anything. So we only have this. So as a result, unrestricted estimator can be written as ZIYI divided by ZIXI. That is the unrestricted estimator. And also, it might be helpful later if we define the influence function now. The influence function originally looks like G transpose W G inverse G transpose W, the moment function of beta 0. This was the influence function, but in our case, it is simply expectation ZIXI in the denominator, and in the numerator ZIUI is the influence function. So therefore, the variance, so the variance normal distribution 0 u VU unrestricted variance equals expectation ZIXI squared, and in the numerator we have UI squared ZI squared. So this was the unrestricted variance. Okay, you may just utilize the results from the GMM chapter. And one more thing here, because we did not use the hypothesis at all, this limit and all the results for the unrestricted estimator is true no matter what H0 is right or not, no matter how H0 or the like exogenous or endogenous X is, right? So far, all the results do not depend on the null hypothesis. Now we are going to think about restricted model. In the restricted model, we have two moment conditions if x was, so null hypothesis is exogeneity of x. So if you take the null hypothesis, you have x as an exogenous. So you have two moment conditions, but we did in problem set 4 that we do not need this condition if the regressor was exogenous. If regressor is exogenous, additional instrument does not do anything. So in this case, it's even easier. The restricted moment is xi yi minus beta xi. Sample moment is xi yi minus beta xi. Nothing special. And again here, because we ignore the second moment, weighting matrix does not matter. We are going to use I. So the criterion function is just its square, same reason. And then the first of the condition will be also pretty straightforward, and you can calculate. The result is OLS. We showed the equivalence of OLS and GMM when X is exogenous in problem set 4, right? So that is the restricted estimator. And let's do a little more. So the influence function will look like this, right? So that's the influence function, and as a result, the asymptotic variance will be like this. Here you have to square it. So that is the asymptotic variance, right? Now then, let's think about Hausman equality. So our test is, so if, let's put it this way, how do we do that? So the unrestricted model always goes to beta 0, right? But the restricted model goes to beta 0 only if H0 is right, because it is utilizing the moment condition from the null hypothesis. So if moment condition is wrong, there will be bias. We learned misspecification bias in chapter 1. So that bias happens if H0 is wrong, okay? So that means these results are true only if H0 is right, right? So all the things, so these results are, theoretical results are based on the null distribution, right? The null hypothesis, okay? That means if you think about the difference is converging to 0 if H0 is right, and it will go to the bias. It will have bias if H0 is like wrong. That's correct. This is Hausman test. Okay, Hausman test is based on this, and that means the idea is reject H0 if the unrestricted estimator minus restricted estimator are different from 0. They should be similar, but if those two estimators are different, then something is wrong. That is the null hypothesis. Okay, then to do that, how do we do this? Idea is the same. We are going to find their null distribution, say it's V Hausman, right? So under null distribution, if H0 is true, we would like to show that the difference converges to a normal distribution. then from here, you may utilize then define, say, t distribution like thing, t test like v hat h over square root n. This converges to normal distribution 0, 1 under h0. So you can apply the standard normal distribution critical value. Or you may utilize Hausman test as a r square, chi-square distribution, VH inverse, same thing. And then it will converge to chi-square Q, where Q is the number of restrictions in the in the null hypothesis, right? So in our case, Q is 1, right? We are utilizing one additional hypothesis in the restricted model under H0. So this process is not a problem. The only problem here is how we calculate the variance, okay? If I will try two ways. Hausman equality says that the variance of unrestricted model minus the restricted model equals variance of unrestricted model minus variance of restricted model. Okay, in our case, it is the unrestricted model was IV regression model, so it looked like this minus expectation ui squared xi squared divided by expectation xi squared squared. So this is the result of Hausman test. Now then what happens if you did not know Hausman test? How can we calculate the variance? The idea is influence function. Of course, under H0. If H0 is true, then we will have this, and that means influence function of unrestricted model minus influence function of restricted model. So as a whole, you are going to get unrestricted minus restricted models influence function. Let's think about this. Unrestricted models influence function was expectation xi zi in the denominator over zi ui, and restricted estimators influence function is this. Okay, then their difference is ui factored out zi over expectation xi zi minus xi over expectation xi squared. Okay, so this is the new influence function. As a result, the variance of like square root n times beta hat un minus beta hat rn equals square root n times 1 over n summation psi u minus psi r using the influence function, and it converges to normal distribution 0 and vh, where vh is expectation of ui minus r squared. This is what we have to calculate, right? Let's see if it's really true. So u square, if you take square of that, so this is zi over expectation xi zi minus xi over expectation xi squared, and you square them. I will ignore u square. U is the same. It does not go away at all. So if you take square, if you calculate that, zi squared over expectation xi zi total square plus xi squared over xi squared square minus 2 times xizi over expectation xizi times expectation xi squared. Okay, and then now let's take expectations. Expectation here, expectation here, expectation here. So then it will cancel out. Okay, so and then if you look at this carefully, the first term does not change. But like here, let's think about this. It is in the denominator is x expectation of x squared, and in the numerator it is minus 2, right? So, but here this term has x squared expectation and then squared again. So you have to square it and then multiply x squared expectation here. And then this is cancelled out. So minus 2 x squared will be cancelling out the previous term. Then you will get this, right? By the way, I ignored ui everywhere. Ui squared, ui. So ui should be here. Ui squared should be here. And then if you imagine that, that's exactly what you get from the Hausmann equality. Okay? So then, let's finally summarize. This is VH. So you can easily calculate VH hat. It is not that difficult. One more thing. I didn't mention. So this is true only under H0, right? So let's think about calculating VH hat. VH is expectation ui squared zi squared over expectation zi squared xi squared minus expectation ui squared xi squared divided by expectation xi squared. Something is wrong. I wanted to write square like this. Okay, so it was wrong. So, we are going to calculate sample average of ui hat squared, zi squared, like this, using sample average of everything, zi xi squared minus like some ui hat squared z xi squared over some xi squared and then square. So this will be your estimator. Okay. The problem here is ui hat. So ui hat is yi minus beta hat xi. Okay. How can we define this? Because you may use beta r or beta r hat or beta u hat. So you have two different estimators. Which one do we have to use? My recommendation is this, because it is more robust. So this is always consistent for beta 0, no matter what H0 does, right? Even if H0 is wrong, still unrestricted estimator is consistent, so it is a safer choice. So I think that's why the unrestricted estimator is used for U. And then as I said, you are going to use the standard normal or chi-square for the rejection rule.